Hello everyone, my name is Roy Jafari, and in this video we are going to have a deeper clustering analysis of the example we started in the previous video I just made. So in the previous video, what we did, we only worked on a segment of the data. Specifically, the world happiness data, we had different years of report, 2010 all the way to 2019. We only separated the year of 2019 and then we performed our clustering task on that 1 year. The reason we did that because we wanted to focus on being able to learn clustering analysis and how we would go about actually meaningfully cluster the data. In this video, we're going to take a stab at the whole data set. We're going to do this using 3 different approaches. The first approach, we're going to include all of the data, and on the second and the third approach, we are going to reduce the dimension of the data set before applying clustering analysis to it. So along the video, I will, once we look at those different ways of going about this, I will also comment on the advantages and disadvantages of these 2 different ways of doing dimension reduction. The first one is going to be a non-parametric dimension reduction, PCA, principal component analysis, and the second one is going to be a functional data reduction, and it's going to be somewhat parametric. And I will discuss what I mean by that. So this video, we are basically going to actually see how a result of clustering would change based on the way we select and pre-process our data, basically. So let's get to it. Alright, so as always, we import the most important modules, and here we take a look at our data. Pay attention here. Now, if we look at our data before doing this part, let me separate this. Copy this. Our data is in a format that each year has its own, column. Basically, we are separating the years based on a column. So we have a long format for recording the years, right? So for us to be able to also include year in a different measurements in different years, we need to have it in a wide format so we can use clustering algorithm on it, right? So here I am using a pivot table, the pivot function of the pandas to sort of like push the year information into the column, so I have a wider data frame. So let's do that here, and now we can see I have, for example, the information of population for 2010 2019 as different columns, and I have all of them, all of those happiness indexes here as well. For me to be able to use this data, I need to be very specific about the attributes I want to include. As you remember, we didn't want to include the attribute population or continent. And here, I only include the happiness indexes, right? So pay attention here. This data frame has a multi-level column. And when I'm including these, first level columns, so these are the first level columns, population and, all of the happiness indexes, I am actually including all of these attributes. So let's go ahead and take a look at this. So once I do this, now I have, not only included all of the attribute, but also I have also standardized all of these measurements, life ladder, log of GDP per capita, social support, and so on and so forth for each of the years. So now the data is ready for clustering. Remember, this data set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times larger than the data set we use in the other video, that we clustered this data only based on the year 2019, right? So now we have 10 times more attributes in this data. So one of the concerns that we have, I mean, the number of data objects that we have here is not that many. We only have 122. And for this case, computational cost is not going to be a barrier for us because the number of data objects is not that many. But if the number of data objects were that many, multiplying the number of the attributes by 10 would mean a lot of computational cost. So just saying that as sort of like a background, so we once we go to the feature, once we talk about dimension reduction, different techniques that we could have done this with, you remember this, that we are sort of like doing a very costly step here because we have so many attributes, right? So let's go ahead and do this. Like I said, it's not going to be very computationally expensive because we don't have as many data. We don't have very many data objects. So we create our Hopkins statistics so we can like check the clusterability of the data, and the data is clusterable. If we keep running this, it's going to be around 0.4. So 0.7. So it's a clusterable data as we discussed. And we also check how the k-means will just cluster. So it does cluster and it works on our data. So apparently everything looks good. But we also want to see if our data shows a consistency in the clustering that it gives us. So we run this a few times, and we see that sometimes it gives us 0.4, 0.5. So it seems that there is something that the clustering algorithm sort of reaches to. So we can see like 0.5. It means the two randomized version of k-means reach the same conclusion, right? So it means that there is something in the data, that there is a meaningful cluster that the algorithm is capable of finding. This is in line with what we saw as the result of Hopkins statistics. We saw our data is meaningfully clusterable. So this is a sort of a confirmation of that. But anyway, we know, once we do know that our data is clusterable, what do we need to do? We need to find the number of clusters. And we have discussed two different methods. So let's go ahead and apply these two different methods on this version of the data as well. We calculate the sum of the squared error for different possible clusters, and we find the elbow in the plot of the line plot of the SSE for the number of clusters. And we can see that we have two elbows here. We have one at 4 and one at 6. So those could be the possible clusters that we have here. But let us also look at the silhouette score. And so once we do this, we look at the silhouette score, which is a little bit different because sum of score error, as we talked about, only looked at the compactness of these clusters. But silhouette score not only looks at the compactness of the cluster, but also looks at the distance these clusters are from one another. So it's a more complex index, and the higher it is, the better as far as the clustering quality. And when we look at the output of this one, we will see clearly when we are at clustering number of 4 cluster, we see an improvement, and then we see a downward movement. So clearly there is a, something about 4 cluster that we see this improvement. And since we also had seen that, we had an elbow on SSE here, so we have overwhelming evidence that using K4 is going to be the most beneficial. So now we are seeing that by changing the data, so we had only used a part of the data 2019, but now we're using all of the data 2010 2019. So we do have more numbers of attributes, but also we see there is a change in the number of clusters that we were able to find. So we moved from 3 clusters to 4 clusters. So we do know that we should use K4, and then we also check if there is consistency in finding the cluster when we have 4 clusters. And we do see that every time we run this randomized algorithm on the data, it reaches the same conclusion, the same clusters, right? It's because 4 parameters are the same. So it doesn't really matter. We don't need to basically control the randomization, because every time it reaches the same output. So once I run this, now I have my members, right? So this is my members, and we also do some centroid analysis, and these are the value for each of those, and it's very overwhelming to look at this without the help of a visual. So we use a visual. Pay attention here. When we are looking at the number, we do the centroids on the original value, but when we want to look at the heat map for our centroid analysis, we look at the actual standardized values. So once we do this, we will see this visual that's going to help us see the patterns in the clusters. Now, if you remember from the previous video, the number of attributes we had were just much smaller. Now we have 10 times more. But since there are a lot of relationship in this data that we had already seen, when we got to know the data, this is not as overwhelming as it could be. We could actually see this visual and meaningfully profile these clusters, right? For example, we do see that cluster 3 on all of these happiness indexes is the highest, also on generosity, and it's lowest on the perception of corruption in all different years. It's highest in the positive affect and the lowest in the negative affect. So we can say this is a very happy cluster. And then we do see that, for example, cluster 2, even though they are among the the lowest on the most of the happiness index, except for freedom to make choices, and also they are at the higher level of generosity, but they are also very somewhat high on perception of corruption. So cluster 2, or we can call them generously happy but crime ridden, because they are very high on generosity. And cluster 1, we do see that they are among the ones that have the lowest happiness indexes on most of the happiness indexes, except for generosity, but they also have high perception of corruptions. So we call them unhappy but generous, and so that's cluster 1, unhappy and generous. Cluster 2 was unhappy. Cluster 1 was happy but crime ridden. Cluster 2 was happy. Cluster 1 was happy with crime ridden, and cluster 1 is cluster 0, happy but crime. Cluster 0. So let's check again. So we have happy but crime ridden, cluster 0. Cluster 1 we have generously happy with crime ridden. We have generously happy and crime ridden, and they're also high. And cluster 2 we have unhappy but generous. They are unhappy but they're generous. And then cluster 3 we have very happy. Cluster 3 we have very happy. So these are based on what we saw in the data, right? So these are the profile that we created. So we go ahead and add this to our data, right? So now we have a column added to our data cluster based on no pre-processing. So as we continue in this video, we're going to create 2 more output of clusterings based on having done 2 types of pre-processing before getting to actual clustering data. Alright, the first type of transformation or data pre-processing we could have done is, instead of using all of the data, we could have done a PCA on all of the data and capture the most informative PCs as far as the explanation of the variation across the data. And the benefit of doing a PCA would be if you had much more data objects for you to be able to afford the clustering analysis, then this would allow you to do this. But here we only had 122, and having had around 100 attributes didn't really matter that much. But for the sake of practicing it, we're going to compare what would happen if we had done PCA before doing clustering. So we go ahead and do the PCA on our Excel, and we do remember when we do PCA, we do want to do it on the standardized data. Remember, because if we didn't do it on a standardized data, again, PCA is going to try to shift the data in such a way that the most of total variation in the data is shifted towards the first principal components, right? And if you have attributes that just have higher variance in the data, right, it's going to be more important in this process of PCA trying to shift most of the variation. So in effect, the attribute that has high variation is going to sort of like dominate the PCA efforts, basically. So because of that, we have used the standardized one to fit to the PCA. So once we run this, we do see that at PC8, once we hit PC8, 8 attribute, 8 dimension, we have explained 90% of the variation in the data, which is great. I mean, like, you know, instead of having to use around 100, which was 90, instead of having to use around 90 attributes, we could be using 8 attributes, and that's more than 10%, more than 90% saving in the computational cost. More than 90% saving the computational cost. Like I said, it's not going to matter as much because we don't have as many data objects, but in case we did, this would be the way to go, right? So here, now we only use PC1 to PC from 8, and we can also take advantage of PCA to sort of see some visual of our data that can tell us how many clusters we have, right? So if I were to do a scatter plot of PC1 and PC2, I would be looking at 50% of the variation in my data by just looking at that visual, right? So this is pretty significant to be able to do this, right? So I do see that, you know, 50% of the variation in data is summarized in this visual. And I can also add a little bit more. I can also go up to 66-70% of the variation by data, but also using color, right? So I can add PC3 as a color to this map. And once I do this, now I kind of see how I had 4 clusters, right? So, you know, these could be one cluster based on their color and, you know, their location. These could be one cluster. These could be one cluster. And this would be one cluster, right? So I do see somehow the 4 number of clusters that I had calculated based on the whole data using k-means. But I can also see it visually here, and that's pretty significant. So let's go ahead and also confirm this by actually finding number of clusters based on this new data. Here, I'm going to use scores. This is what I extracted from the PCA. So these are basically the PCs that we extracted. So I use that to find the number of clusters. So once I do this, let's see. It's going to run much faster because I don't have as many attributes here. And then once I run this, I do see a similar effect. I have an L bond 4 and L bond 6, somewhat an L bond 3. And then I also do the FS score, silhouette score, and see what's gonna be for that one. And I do also see the same, upward improvement on the 4 number of clusters. But I do also see that if you remember, when we use all of the data, there was like an upward movement on number of cluster 10, but here it's on number of cluster 9. So some stuff changed here, but we do see a consistency in the results we're getting. So the number of clusters are obviously 4. So I go ahead and do the clustering based on the 4 and see every time it reaches the same values. And then, of course, I come up with the clusters. So these are the cluster. I do some centroid analysis for this new one, and pay attention here. When I do the original values are just from the original values. I don't need to show PCs, right? So I can look at these values based on the original values and see what's happening here. But now I can also check the centroids for these clusterings, right? And I can see that, you know, the majority of the reason that clusters are created are due to PC1, PC2, and PC3. And as we move down the line, the importance of these values are not shown. And we can also sort of accept this because, you know, if you remember, the amount of variation these PCs were showing, it was not that significant, right? So if you come here, we see that, you know, 50% variation is explained here, and then you have 15%, and then 7%, 5%, 4%, 2%, 2% and 1%, and now almost 2%. So the fact that this has more importance in the formation of the cluster is a good news, right? So that's something I wanted to make sure that makes sense. I could have, before you know, creating this, I could have sort of like standardized the centroid analysis to see what's happening here. And once I do that, it's not really giving me anything meaningful because the PCs are not anything meaningful. They're not attributes. So I have found the meaningful cluster in these dimensions, but what I haven't been able to do is I can't do it, is to profile them, right? So this is as far as I can go because these PCs don't have intuitive understanding for me. And I also can check that as you move from PC1 to PC8, the range of your attributes from min to max decreases, right? So you start from -2 to 3, and you go to all the way to 0.2 to 0.7. And that's why the first PCs are more important in the creation of the cluster than the last PCs. So we go ahead and create our, you know, add our members as a new cluster. But here, like I said, what you have is cluster PCA, right? So you only have numbers. You have cluster 0, 1, 2, 3. And that's just the way it is, right? Because we don't know, we can't profile them because we did PCA. So here we, you know, look at the relationship between these clusters, and we do see that it is finding the same clusters that we found using the whole data set, right? Without having done PCA. But here we did find those values, but we were not able to use PCAs to profile them, and that's the disadvantage of PCA. PCA would have helped us if we had a large number of data objects, would have helped us in computation, but it would also not help us with the profiling because PCAs are not intuitive. Another way we could sort of help to keep our intuitiveness and at the same time cut back on some of the computation would be to do functional data reduction. In fact, functional data reduction can also sometimes, and in this case also, can help you to sort of massage your data in such a way that the patterns are easier for the clustering algorithm to find. So you have to just accept, you know, the data massaging part because you will need to see examples of this to reach a higher level of understanding on this. But just let that be in the back of your mind that not only functional data reduction can help you reduce your data, but also it can also be used as a massaging your data, so the patterns that are in your data that it's important to you are easier for your clustering algorithm to pick up on and cluster your data based on. So let's look at the functional data reduction, and we'll see what I mean perhaps by looking at this. So each of these attributes, each of these, you know, happiness indexes, we could look at them as one unit of information, right? So we could look at this, for example, for USA life ladder from 2010 to 2019. This is an ups and downs of, life ladder for USA, and every country for each of these indexes have something like this. So why don't we, instead of using all these data, why don't we just extract two features from this visual that pretty much summarizes what's happening here? So one of the features that we could sort of use is the slope of the regression fitted data on this data, right? So we could use the slope as somewhat tells us what's been the change of life ladder for US, right? So this is the slope that tells us that with this slope the life ladder has been decreasing. And then also we could also include the mean, which is sort of a summary of what's been the life ladder for US in these different years. So we could do this for all of the different happiness indexes for all the countries, and then we would have a data that is smaller but also keeps all of the sort of like a meaningful information or the intuitiveness of our data. So here I created a pre-processed DF as a placeholder, and then using some Boolean math and some other modules such as in linear regression, I complete this pre-processed DF. And once I run this, I do see that I have the mean and the slope of all of the happiness indexes for all of the countries, right? So this is the pre-processed data. So now here, instead of having cut back around 90% on the amount of attributes, I have cut back around 80%, right? And now here I have 18 attributes. With PCA, I had only 8 attributes. And with the whole data, I had 90 attributes. And I do have a little bit more, but at the same time, I have kept all of the intuitiveness of my data. So here, I can just check that if my calculation was correct. For US, the life ladder mean was 7.0, and the slope was negative 0.03, and I think that was the same thing that we calculated here. The mean was this one and the slope was this one. So my code here is doing this correctly. I mean, this is just a check that these values are correct. So now that I have my data pre-processed, now I don't forget that I need to standardize data before using it. So this is my X's, and then I find the number of clusters based on the sum of a squared error. And let's see the visual. I do see again another elbow on 4. And then also let's look at the silhouette score. And on silhouette score, I do see on 3 and then on 4, I do see a decline. And there is a uptick on the 11. But since I have an elbow here on 4, and at the same time I've been using 4 clusters, and I want to sort of compare it with other clusters I've had, let's go with k-mooc equals to 4. So I do see that after me massaging the data, now there are some different patterns that k-means is picking up on, and it's not the same values or the same patterns or the same clusterability that we had using PCA or the whole data set. So some of the things that has changed here, we cannot start seeing it. So let's go ahead and use k equal to 4 for the reason I just said. And then once I do this, I do see that again this is picking up on the same patterns in the data. So I go ahead and do this, and now I can also do the centroid analysis. With the centroid analysis, now I have a much more sort of like manageable visualization I can look at, right? So as far as the visual that we had for the first clustering, the names could be applied here as well. So we have the very happy cluster here. So this is a very happy, so this time is just clustering 2, and then we have happy but crime ridden. We have this one, cluster 0, happy but crime ridden, and then we have unhappy but generous here, unhappy but generous. They are unhappy but generous, cluster 3. So we have that. So let's go from the top. So cluster 0 is, we can see that they are high on crime, and they are somewhat happy but not generous. So we are on happy but happy with crime ridden. So this is cluster 0. Cluster 1 is again somewhat happy but generous. So we have generously happy but crime ridden. So this is cluster 1, and then cluster 2 is very happy, and cluster 0, cluster 3 is unhappy but generous. And also that unhappy but generous also have a very high slope on negative affect. Means their negative affects been changing for the worse. So we do see that the mean values have more importance in the formation of these clusters than the slope, and this in itself is a pattern we are seeing here because we took the time to massage the data, right? So these slope is not a distinguishing factor in the cluster, is because the whole world has been moving toward the same direction, and it's not very important as far as seeing the difference in the country. What we see the difference in the countries is because of actual differences that these happiness indexes have. It's not because of the amount of change they've had. So this could tells us that there's not a lot of relationship as far as the different countries having had different progress in these indexes, and is in itself a valuable pattern to see, right? So that's why that piece of data massaging I was talking about is sort of like showing itself here. So we go ahead and cluster our data. We add this cluster to the data. Now we have a cluster based on the functional and also cluster based on no pre-processing. And now we can see the relationship between them. And once we do this, we do see that, there is, for the most part, they are sort of like, there is an overlap between them, but there are also some changes. So for example, on the very happy one that we use for no pre-processing, some of the very happy ones that we also saw in the clustering functional, some of them are actually generous, happy, but crime ridden. So we sort of like have a difference here. Also, we have a little bit of difference on these attributes. So, we are getting at the same thing, but here, because we massage the data and like we did some functional later reduction, the result is a little bit different. And perhaps I would claim that the clusterings result for the one that we did functional later reduction is actually more reliable, because we took the time to take out what's more important for us. The progress was important for us. We have a extracted feature for it, and also what it is, what's the state of that country based on each happiness index, which we extracted the mean for that. Alright, so what we did in this video, we basically did the same clustering task we had done in the previous video, but in this one, we took it upon ourselves to include the whole data. In the first video, we only had included the data for 2019, but in this video, we included the whole data, and we saw what would happen if we included the whole data without any data pre-processing, and if we had done PCA, and if we had done functional later reduction. So we saw the differences between them, and we discussed their advantages and disadvantages, and we actually saw how this could be